Polymers are widely used in daily life because they are durable, low cost, and versatile, especially in packaging and consumer products. However, most polymers are highly resistant to natural degradation, which causes them to accumulate in the environment over long periods. One of the main factors that initiates polymer degradation is ultraviolet or UV radiation from sunlight. UV exposure can trigger photooxidative reaction that break polymer chain, produce free radicals, and cause chemical and structural changes. Over time, these processes may lead to fragmentation of plastics into smaller particles. Different polymers respond differently to UV radiation depending on their molecular structure. HDPE has a simple aliphatic backbone and is more susceptible to photooxidative degradation. PET contains aromatic rings which provide better UV stability. In contrast, NBR has unsaturated bonds that are more sensitive to UV exposure, leading to chain scission and cross-linking. In this study, FTIR spectroscopy was used to monitor chemical changes during UV aging, particularly the formation of oxygen-containing functional groups such as carbonyl groups, which are key indicators of photooxidative degradation. Three types of polymer were used, which are high-density polyethylene or HDPE, polyethylene terephthalate or PET, and nitrile butadiene dropper (NBR). These samples were obtained from commercially available consumer plastic products. Before testing, all samples were cleaned using distilled water and ethanol to remove surface contaminants. Air dry at room temperature and cut into uniform sizes to ensure consistent UV exposure. For the UV exposure procedure, the prepared samples were irradiated using a UV lamp at a wavelength of 254 nanometers for 24 hours. The samples were placed at a fixed distance from the UV source to ensure uniform irradiation. Unexposed samples were kept in the dark and used as control sample, while temperature and humidity were maintained constant throughout the experiment. After UV exposure, chemical changes in the polymers were analyzed using Fourier transform infrared spectroscopy with ATR mode. FTIR spectra were recorded in the range of 4,000 to 400 inverse centimeter and compared with non-UV samples. Changes in characteristic absorption peak, particularly in the carbonyl region, were used to evaluate the extent of UV-induced photooxidative degradation. For HDPE, the FTIR spectra of both the UV exposure and non-UV samples showed strong absorption band in the range of 2915 to 2848 inverse centimeters, which correspond to aliphatic CH stretching vibration. This indicates that the primary polyethylene backbone remained largely intact after UV exposure. However, noticeable changes were observed in the UV-treated HDPE sample. A slight decrease in peak intensity and minor peak broadening were detected, particularly in the CH stretching and bending regions. These changes suggest an increase in structural disorder within the polymer chains, which is commonly associated with UV-induced degradation. In addition, a weak carbonyl absorption band appeared in the region of approximately 1700 to 1750 inverse centimeter. The presence of this peak indicates the early formation of oxygen-containing functional groups such as ketones and aldehyde. Resulting from photooxidation, UV radiation provides sufficient energy to break C and CH bonds, generating free radicals that readily react with oxygen. This chain scission process lead to a reduction in molecular weight which explain the observed increase in surface roughness, loss of transparency and increased brittleness of the UV exposed HDPE sample. Overall, the degradation observed in HDPE can be classified as early stage photooxidative degradation, primarily limited by the relatively short UV exposed time of 24 hours. For NBR, both UV exposed and non-UV sample exhibited a distinct absorption band at approximately 2237 inverse centimeters, which is characteristic of the nitrile group present in the acrylonitrile component of the polymer. This confirms that the main functional group of NBR were retained after UV exposure. However, following UV irradiation, noticeable changes were observed in the NBR spectrum. The nitrile peak became broader and less sharp, indicating changes in the local chemical environment surrounding the nitrile groups. Additionally, a reduction in intensity was observed in the double bond C stretching region between 1500 and 1600 inverse centimeters, which correspond to the unsaturated butadiene segment of the polymer. This observation suggests that UV radiation preferentially attacks the unsaturated bond in the butadiene units, leading to both chain scission and cross-linking reaction. Chain scission reduces molecular flexibility, while cross-linking increases rigidity within the rubber network. This combination explains the reduction in elasticity and increased stiffness observed in the UV-treated NBR sample. Furthermore, the fingerprint region between 1000 and 500 inverse centimeter become less defined after UV exposure, indicating structural rearrangement within the polymer matrix. The absence of strong new oxidation peak suggests that the degradation was moderate and had not progressed to severe oxidation under the experimental condition. Aku macam malas nak. For For PET, the FTIR spectra of both UV-exposed and non-UV samples showed strong and well-defined absorption bands around 1735 inverse centimeters, corresponding to ester carbonyl stretching vibrations. Additional characteristic peaks related to COC stretching and aromatic C double bond C vibrations were also observed and remain sharp after UV exposure. Only a slight increase in the intensity of the carbonyl peaks was detected in the UV-treated PET samples, suggesting minimal photooxidation or limited ester bone cleavage. Importantly, no significant peak shift or new functional group were observed, indicating that the overall polymer backbone remained chemically stable after UV exposure. The high resistance of PET to UV-induced degradation can be attributed to the presence of aromatic rings within its molecular structure. These aromatic rings are capable of absorbing and dissipating UV energy more effectively, thereby protecting the polymer chains from its extensive bond breakage. This chemical stability is consistent with the visual observation where the PET samples retain their transparency, smooth surface, and mechanical integrity after 24 hours of UV irradiation. Among the three polymers studied, PET demonstrates the highest resistance to UV degradation, highlighting the important role of molecular structure in determining polymer stability under UV exposure. This study demonstrated that UV irradiation at 254 nanomicrometer for 24 hours induced different degrees of degradation in HDPE, NBr, and PET depending on their molecular structure. HDPE exhibit early stage photooxidative degradation resulting in increased surface roughness, opacity, and brittleness, while NBr showed moderated degradation involving chain scission and cross-linking, leading to reduced elasticity. In contrast, PET displayed the highest resistance to UV exposure, with minimal chemical and physical changes observed. Overall, the FTIR results confirm that polymer containing aromatic structure possess greater stability against UV-induced aging compared to polymers with aliphatic or unsaturated backbones.